So we've seen a case now where the overhead dominates, and we've seen a case where the recursion dominates, and it's the leaves, the number of leaves of the recursion tree that kind of determines the order of growth of the algorithm. The question is there something in between? And it turns out, in a sense, there is. In a fairly limited sense, but in some sense there is. So let me call this the balanced case. In the balanced case, what we have is something that looks like this. And in a very specific sense, when you're living in a balanced case recurrence relation, the overhead is exactly balanced right with the recursion. So what do we have? We have something like the following. So this is a classic balanced case recurrence relation. Right. What we're doing here is we have two recursive calls on half the size of the input and a linear amount of overhead at every step. Okay. So what this ends up looking like, if we chase this thing out, if we analyze this all the way down, is what this ends up looking like is T of n is big theta of n log n. Okay, and so it's not obvious why this is better than the others, at least just by looking at it right here. But it turns out that this is a sharp case in a precise sense, in the sense that if we made the overhead any bigger, then the overhead would dominate. But if we made the recursion any heavier, then the recursion would dominate. And by being somewhere here in the middle, we're able to make things balanced in some sense. All right, so all these cases, these three cases, can all be summed up by something called the Master Theorem. So let me give you the Master Theorem. I'll interpret it just a little bit, and then we'll close for today. So this is called the Master Theorem. And so the Master Theorem applies to the kind of the core divide and conquer recurrence relation. And so here's how it goes. So we're going to let T of n be given by this core recurrence relation that we've been talking about today. So T of n is a times T of n over b plus f of n. And so a here is greater than or equal to 1. B is strictly greater than 1. Pause for just a moment and think to yourself why b has to be strictly greater than 1 rather than greater than or equal to 1. Right? What would go wrong if b were equal to 1? And then we're going to define the following. We're going to define c, a third thing, as the critical exponent, or we'll call it the critical exponent, and it's defined as in the following way. So c equals log base b of a. Base b of a. And I know I've talked a lot about how the base of the log doesn't really matter. In this case, it does. Right? So you have to make sure that you get the base of the logarithm correct in this case, or your critical exponent will be wrong. Right? So this thing here is called the critical exponent. All right, and the critical exponent turns out to define very precisely what the threshold is between overhead dominating and recursion dominating. Okay, so here are the three possible cases, or at least the three cases that we'll talk about today. There are some subtleties that arise in a few of these that you can go and study on your own or talk to me about in office hours. So one, we'll call this the overhead dominating case. So this is the f of n dominant case. So suppose f of n, so here if f of n is in big omega of n to the d, okay, so this is a subtle definition, right? So stick with me here. So f of n is in big omega of this polynomial of n to the d, and now you look at it and you say, where's d? Well, here's d, right? D is anything strictly greater than c, right? Where d is greater than c, okay? And so there's a couple other ways I could write this, right? I could say, i.e. d is greater than log b log base b of a. Okay, or I could say b to the power of d is greater than a, right? And this is equivalently, so all these three are equivalent, or b to the power of d is greater than a, right? All three of those are equivalent. The first one because I just rewrote c as my definition, and the second one because I played with my log rules and got it to say what I wanted it to say there. Okay. Basically, I raised both sides to the power of b, and the answer came out right. Okay, so what does this mean? This means that if the recursion term is bigger, in a kind of a strict sense, is bigger than a polynomial with this critical exponent, then we get the following. Then t of n is big theta of f of n. Okay, so all this is saying, right, the very condensed version of this is saying that if f of n, right, if the overhead term grows faster than a polynomial with the critical exponent, right, than n to the c, and faster in a strict sense, then our overall recurrence relation has the same complexity as the overhead, right? Then the overhead is all that matters, right? And that's what the conclusion here says, is that if the overhead is big enough, it runs the entire show. Okay? So case number 2 is what I'll call the balanced case. So this is, I'll just call this balanced. Balanced works like this. If f of n, again we have a condition on f of n. So if f of n is big theta of, now here's something a little bit strange, but we'll go with it. If it's big theta of n to the c, so a polynomial of degree the critical exponent, that log base b of a, times some number of logs. Okay, so here's an odd thing I'll add in, times log n to the power of k. Right? So I can take the critical exponent and perhaps times some logs, right? So here k is something greater than or equal to 0. So I don't have to take any extra logs. You know, I can let k equal 0 and just say if f of n is big theta of n to the c, right, or n to the log b of a, then what do I get? I get only a log slowdown. Okay, so here's what that means. Then t of n is big theta of n to the c, n to that critical exponent, times log n to the k plus 1, right? So the same complexity as f of n times one extra log. So log n to the k plus 1, right? So what does this mean? This means that if f of n is tuned exactly right, if f of n is essentially tuned right to that polynomial with the critical exponent, then I get, then the overall recurrence is the same speed as the overhead with merely a log slowdown, right? So how do we write this? T of n is the same as f of n with a log slowdown. Right, where do I get this idea of a log slowdown? I get it from the plus 1, right? The k plus 1 right there tells me, you know, it's the same complexity as f of n times 1 log, which is a minuscule slowdown. Okay, so there's our balanced case, and then in the third scenario we have the recursion dominates, and so I can say this is the recursion dominant case. Okay, so the recursion dominant case is the following. Suppose f of n is big O, not big theta, big O, right, is upper bounded by n to the d, where now d is anything strictly less than the critical exponent, right? So d is less than c. Another way to write this is i.e. d is less than log b of a, or b to the d, so b to the power of d is less than a. Right? Those are all equivalent ways of writing this condition. And basically what this means is that the overhead is strictly faster, right? It is strictly upper bounded asymptotically by this n to the critical exponent. Then what do we have? We have then t of n is big theta of n to the d, n to the c, right? And this is the case that we looked at where we had all of those leaves of the recursion tree, where the leaves of the recursion tree were what was running the show, right? It was that was slowing us down. So here's the picture, right? This is a lot of stuff, and I strongly encourage you to, take this, print it out, have it in front of you, and every time you run into one of these recurrence relations, sink your teeth into it, figure out what is C, figure out what are these logs doing, what is big O of what's big theta of what, et cetera, and then reference this picture, right? So this is the picture. So given this recurrence relation, first compute the C, right? First compute the critical exponent, right? So if you're given t of n equals a times t of n over b plus f of n, the first thing is compute c. So compute c first. C equals log base b of a. And then picture plotting n to the c, right? So here is my n to the c. Right? It's some function. So this is n to the c, right? And now figure out how f of n relates to that, right? So suppose, for example, that f of n is up here, right? Suppose f of n is up here. What does that mean? Essentially, that means that f of n is big omega of n to the c, right? So if f of n is big omega of n to the c, essentially, right, this is what we have, then what does that tell us? Well, that tells us, this is the case that the overhead is dominating. So then we look back at the theorem and we say, what does it mean if the overhead is dominating? Well, it means that the overall recurrence relation has the same complexity as the overhead, right? As simple as that, right? What do we get? Well, then t of n, the whole thing, is big theta of f of n. And all we needed to know is that f of n was asymptotically worse, right? Grew faster asymptotically than n to the c. Now, suppose you have the situation that f of n is way down here, right? So, I'll label this case 1, and I'll label this case 3, because it corresponds to case 3 of our theorem. So this is f of n. What happens if f of n is way down here? Well, this corresponds to the idea that f of n is big O of n to the c. Essentially, that's what this means, right? That n to the c is dominating f of n. F of n is not big enough to kind of compete with this critical exponent polynomial. So that means it's big O of n to the c. Now I scroll up to my theorem and see which case has that, and that's here. And in that case, I end up with complexity equal to big theta of n to the c. Right? So that tells me something about my overall recurrence relation. And it says this is big theta of n to the c. Now, what's the middle case? I guess I'll do the middle case in black. So the middle case is that f of n exactly matches, or is the same complexity class as n to the c. Right? So there's f of n. And this essentially is case 2, the balanced case. And so if f of n, and notice I'm leaving out all those logs because they're not often going to come up. So if f of n is big theta of n to the c, then what do I get? Well, I get t of n is big theta of n to the c, log n. And if I'm very precise and I want to be very, very painstaking about it, it's the log base b of n. Right? which changing logs is only a constant factor change, so that doesn't make a big difference, but nonetheless, there we have it. So there's case 2, blue is case 1, green is case 3. Okay, and that's the snapshot. That's the snapshot of the Master Theorem. And there are a few extra subtleties that are involved when you get into those log multipliers in part 2, but for the most part, this is what we have.